Just one more time, if you could somehow take the time to look in your folders, make sure that you have only one lunch ticket, one banquet ticket. It's all you can eat lunch, all you can eat dinner, so you don't need more than one ticket. You don't need that. Something, how many people would be interested? If we can get the speakers to kind of agree to this, if they will put some of the materials, if they have either images or whatever online, we'll try to set up a post-mortem to the conference and try to do a summarization of all of the key points on each talk, put it online and make the announcement out to you. So if you want to pick up more information on how to understand some of the charts, graphs, it'll give you a chance to do it as a learning experiment. So if the speakers are willing to do that, we'll be willing to put that online for everyone. Okay. The next speaker is one of the luckiest people as far when it comes to storm chasing that I know, except for the fact that I think he storm chased with Gil Sabensky last year, and I'm sorry about that, Gil. No, but it doesn't matter what happens. It seems like Greg's always stumbling onto a couple of supercells and tornadoes, whether he's in Indiana and just happened to be out at a conference and he looks outside and goes, oh, that looks interesting. And I think one of the reasons he's so lucky is because he's doing a lot of algorithm development, and he's probably taking the raw radar data and then getting all the good stuff for himself and putting all the rest of the garbage out in the line. Greg works at National Severe Storms Laboratory. He's got a lot of different titles. I'm not sure exactly what it is that he does there, so I asked him just before break, and he said, well, I'm a meteorologist. So I'd like to offer you Greg Stumpf, meteorologist from National Severe Storms Lab, and he'll be talking about radar algorithm and development for the WSR 88Ds. Greg.
Thank you, Paul. Can everyone hear me okay? What? Gilbert can, that's good. Eric, you can go ahead and switch on the overhead there. I'm going to attempt to do this talk on PowerPoint. I've done it a couple times before with success, but just in case, I do have my MuGraph backups here. So, the title of the talk is The Radar Algorithm Development and Testing at NSSL. And that's sort of my title there too as well. I work at NSSL. I'm being paid by SIMS, which is a cooperative institute at Oklahoma University. And the team that I lead up is called the SWAT team, which stands for Severe Weather Warning Applications and Technology Transfer. As Paul was alluding to, he was hoping we'd all put our information on the web. What I'll do when I do get back to Norman is go ahead and transfer this entire presentation to the web, and you'll find it somewhere under the news section of our SWAT homepage. So I'll give you some time to write down that address because I don't have any handouts. The second address I have under there, and I hope I got this right. If I didn't, you'll find a link to it on our SWAT homepage, is a page that we're starting to develop right now that shows a bunch of different cases of WSR88D data of different kinds of severe storms. Right now our primary focus is in more along my line of algorithm development, and that is mesocyclones and tornadoes. We have on this page a whole slew of different kinds of storms, low-top supercells, supercells caused by tornado or tropical cyclones, the bow echo type of supercells that Ron was talking about earlier, tornadoes out in California, severely tilted supercells, some cases up in Minneapolis area. So it's a real interesting site to check out. So probably you've all gotten enough time to write that down. I'll move ahead to the meat and body of the talk. First I'll outline what I'm going to talk about. First I'll talk briefly about the history of algorithm development at NSSL. Then I'm going to spend a sort of the meat of the talk on the actual current algorithm development that's going on right now. And we'll go into a little bit of the details of what radar algorithms are and the different algorithms that we have developed. We'll talk about testing and also the future of algorithm development at NSSL. So, way back when Chuck and Al were just starting to chase in central Oklahoma, some of the scientists at NSSL were also starting to develop some of the earliest storm detection algorithms. Some scientists also at AFGL, which is near Boston, and some other institutions as well. I don't want to steal away from some of their thunder, but a lot of it done at NSSL. In the early 70s, we had the early storm cell identification and tracking techniques were developed. And then in 1973, on May 24th, I believe, the Union City, Oklahoma tornado happened, and the TVS, or tornado vortex signature, was first discovered in real time on a Doppler radar. In the late 1970s and early 1980s, we began to develop the early mesocyclone detection algorithm. And here's a picture from an old archaic radar screen from NSSL. This is a radar that NSSL operated in the 70s and 80s and somewhat in the 90s as well. And what we've got here, that circle is actually not the detection from the algorithm, but just the cursor placed over a mesocyclone. Also, during this time period, NSSL began to develop the gust front algorithm. But as the early to mid-1980s started to come about, a lot more algorithm development started to happen. The TVS algorithm, tornado vortex signature, was developed. This was the algorithm that made it into the current NexRad that's out there right now. And let me emphasize this, and I'll come back to it later, that this algorithm was actually developed as a placeholder. And the new TVS, or TDA, will be deployed to the field sometime this summer. Mesocyclone algorithm testing began on a central Oklahoma data set. The development of the storm series algorithm that's in the field, storm tracking and all those things. A hail index algorithm to try to determine the probability, basically a categorical probability at the time, sort of a yes, no, maybe type of thing was developed. An upper level divergence algorithm, a velocity de-aliasing algorithm. And in the last year of the 80s, 1989, the first NexRad radar, or WSR-80AD, was operating in central Oklahoma with these algorithms on there, and we wanted to go out in the field and see how well the radar and the algorithms are doing. So we conducted a test called the IOT&E, in which storm chasers went out and actually went into rain cores, tried to determine hail sizes and things like that. Now, they didn't do very well in trying to find tornadoes and storms because there weren't that many to find in that year, unfortunately. There are some limitations, though, to this early work. Of course, back then, computers were small and clumsy and slow. And the other thing is that most of the Doppler radars were research radars, and they're sitting in Oklahoma, central Oklahoma. We had a couple up in Colorado. I believe there was one in central Illinois and one out in Massachusetts as well, but there weren't very many Doppler radars around the country, so most of these algorithms were developed based on the kinds of storms that we knew about on Doppler radar. And most of those happened right here, a term we like to call being Oklacentric with our algorithms. Things have changed. Another offshoot to our work is that we've developed an algorithm for aviation interests for the Terminal Doppler Weather Radar, or TDWR, which is it's a less powerful radar, but it's one that's situated near airports, and it's scanning a sector over the airport basically to warn pilots of wind shifts, runway changes, and dangerous gust fronts. So we did those refinements in the 80s as well. But now that NexRad is here, the OSF Applications Branch, the OSF is the Operational Support Facility for the National Weather Service. They're mostly supporting the radar, but they're doing some other things as well. They have been tasked to conduct proof of concept testing of new algorithms, and they fund us to develop these algorithms. When we do develop an algorithm or have an idea for an algorithm, we have to go in front of what is called the TAC, the Technical Advisory Committee, They're the people who set the priorities for the development, research and development for these algorithms, and they recommend new algorithms to the field. So we'll go up with an idea. They'll say, sounds like a good idea. You guys pay for them to do this. Once we've done it, we go back to them and say, here's what we found. This is the new algorithm we have. Will you recommend this to go into the system? Our present customers in algorithm development. Well, our number one and primary customer is the National Weather Service, of course with the WSR-80AD and severe weather warnings primarily. We also have a secondary customer, the Federal Aviation Administration. Now they're using the TDWR radars, but they're also using the 80ADs as well for en route air traffic planning as well. We're starting to do some work with the Department of Defense, and we're actually starting to dabble a little bit with some private industry collaborations as well. One such private industry was with the Salt River Project, which is a large power company in the central Arizona area. And that's where some of our real-time operational testing of algorithms actually began, and I'll be getting to that too. Well, one of the unique things we have at NSSL in developing algorithms is we not only have experts who know how to program algorithms, but we also have science experts in the same building as well. People like Chuck and Eric and others who are actually the people doing the basic research that feed into what we call our development pipeline to the eventual end product for the user. We've got the basic researchers, we've got people doing applied research and their understanding relating the signatures to the weather phenomenon. Then people like me and others who are developing applications, detection and analysis techniques, or the algorithms. Then we evaluate those algorithms. We do that offline, meaning we look at data in-house and see how well our algorithms are doing. But we also go out in the field and test these algorithms in real time. And finally, we have a user group that's actually comprised of some National Weather Service meteorologists, and Ron is actually on our user group. And this whole pipeline feeds back. Our users see how well our algorithms are doing, and it finally comes back to the whole process. All right, what I'm going to do now is, for some of you who don't know much about algorithms, I'm going to get into some of the basics here. And I'm going to sort of skim the top here, so there might be some things that I miss, that I leave out, but I'll try my best to fill up the time. And the first thing we're going to talk about is WSR-80AD data. And there's actually 3 moments, what they're called, of data that come from what's called the level 2 data stream. The first moment is reflectivity here, which is basically intensity, of course. There's the velocity moment, and in this case we have red colors, which are depicting velocities blowing away from the radar, which is way off in the corner up there, off the picture, and green colors representing flow toward the radar. The third moment is spectrum width, which is basically a measure of the turbulence in the atmosphere. It's actually sort of, an easier way to say it is, it's sort of the standard deviation of all the velocity samples that are being collected within each one of these little boxes. This fourth picture I have on here is not an actual base moment data, but it's a derived data from the velocity field, and that's basically storm relative velocity, which is the more popular way to be looking at velocity in operational terms, and that is the storm motion has actually been subtracted out of the velocity data. In this particular case, there's not much difference between the velocity and storm relative, and I wanted to pick a case that was contemporary. This happened in Oklahoma just last week. So there are limitations to Doppler radar that we have to contend with when we're looking at just the raw data and when we're developing the algorithms. For example, the Doppler radar, or the 80AD, is collected in discrete elevation scans in its volume scan. So that means we're only cutting through sections of the storm. We're not seeing an entire 3D picture, but just sort of plates through that storm. And one of the problems with that is that the radar only scans up to a certain elevation, 19.5 degrees. So if there's echo above that, you don't see it. That's what's called the cone of silence. It is not the calm before the storm, as in the movie Twister, by the way. Also, the radar scans as low as 0.5 degrees. So that means even if the Earth were flat at some distance away from the radar, that beam's going to be over the ground. But we know the Earth curves, so that beam's going to even be higher above the ground. So we have that problem. With distant storms, we don't get to see much of what's going on underneath. And that could be a big deal, and Eric's going to talk a lot about that tomorrow night when he discusses some vortex findings. These volume scans take time. In precipitation mode, they're 5 to 6 minutes long, and there can be some very rapid evolution in the storms in that time. Ron showed some cases where tornadoes developed out of leading edges of bow echoes within 1 or 2 volume scans, but we've seen cases where it's happened within that 5 or 6 minute window and gone away even. You have the Doppler dilemma. Gosh, 2 words. I could say so much on this, but basically what this means is that you either have a lot of velocity folding or a lot of range folding, and we're actually trying to find ways to mitigate that right now. There's the beam width problem. That is, the further away you go from the radar, the beam is still 1 degree wide, but that represents a larger distance in space. 60 miles from the radar, the beam width is 1 mile wide. Flow perpendicular to the radar beam with Doppler velocities, you can't see flow going perpendicular across the beam. It comes out as 0. And finally, we have ground clutter problems. They're not as bad now with the 88D. The objectives of NSSL algorithms. First one, diagnose the present storm structure and its past evolution. 2, to provide warning guidance information. For example, there's a 30% chance of severe hail with this storm. And 3, to provide short-term prediction of severe weather occurrence. For example, there's an 80% chance of a tornado in the next 20 minutes. You'll notice we have probabilities here. That's something, and Chuck's raising his hand in the back, that's something that we're trying to migrate to, is to get away from the categorical description of storm, yes or no, because we really don't know yes or no. There's some middle ground in there of what's really happening. Before I get into the actual algorithms and describing what algorithms are, let me describe real quickly what the Radar and Algorithm Display System is, or RADS. This is a display system we developed at NSSL to help us look at algorithm data overlaid on the radar data. And it's actually migrated into an operational test system that I'll talk about toward the end of the talk. I want to introduce this now because a lot of my figures use RADS. What is RADS? Well, it's got images, which are the radar data, velocity, reflectivity, and so forth. Tables. For each algorithm, we'll display a table like the cell table, which will describe certain attributes about each of the cells that the algorithm is detecting. And the nice thing about the tables in RADS is we have them sorted based on storm severity, and we have color coding on some of the numbers just as heads up when numbers reach certain, high numbers. I've said numbers 3 times, sorry about that. I don't want to use the word threshold because then Chuck will do this. Overlays, those are the algorithm outputs. We'll see some of those in a bit. Trends and time height trends. This is something that Ron showed actually in some of his analyses of the bow echoes, but we've actually, for the algorithms, automated this so the user can actually pop up and look at say, the trend of maximum reflectivity with a storm. We can do cross sections, and we can do loops, and we have a multi-panel display that's similar to the 88D4 panel display, but we can display up to 8 panels, and there's a little more flexibility with that. All right, I'm going to talk about NSSL's Big 5 algorithms. These are the 5 algorithms that we've taken the time in the last 5 or 6 years to really spend a lot of effort on developing for the WSR88D. And I'm going to be referring to them by their acronyms here throughout the talk. The first one is the Storm Cell Identification and Tracking Algorithm, or SCIT. Next is the Hail Detection Algorithm, or HDA. Both of these algorithms have already made it to the field. They are now in use at the National Weather Service. Next, we have the Mesocyclone Detection Algorithm, or MDA. That's the one that I have been developing for the last 4 years. We have the Tornado Detection Algorithm, or TDA. And finally, the Damaging Downburst Prediction and Detection Algorithm, DDPDA. Some algorithm basics. Each of these algorithms goes through 4 dimensions of analysis. And I'll show examples of these after I describe this slide. In the first dimension, we're looking out along the radar beam. So we're trying to determine what's going on along the radar beam. Radial segments, as we call them. In the second dimension, we're looking at horizontal association of these one-dimensional segments. So those are elevation scan features, so one slice through the feature. Next, we do a vertical association, that's the third dimension, and those are volume scan detections. So now we're trying to piece together these 2D slices. And then finally, in the fourth dimension, we're tracking them in time. So we have a 3D detection on one volume scan and on the next volume scan, and we try to associate those. 1D segments. Here is an example of one. This is from either the this is from the mesocyclone algorithm. And what we're looking at here is a trace of Doppler radial velocity with respect to azimuth. So think of the radar scanning this way, and at a constant range, for example, 75 kilometers from the radar, at each angle, it's detecting a different radial velocity. Well, in this case, what we're seeing is increasing radial velocity with increasing azimuth. That's cyclonic shear. So what we have defined right here from this point to that point is a radial shear segment. That's the minimum velocity, the maximum velocity. You can find what's called the delta V, velocity difference across that. You can measure the length from here to here, and so on and so forth. You can do the exact same thing with reflectivity. I don't have a figure for this, but just imagine a little spike in reflectivity here, and that's in range. You've got a reflectivity segment. Imagine a whole bunch of those. Whoops. Well, let's go ahead and discuss this. Okay, let's imagine a whole bunch of these segments here, velocity segments, and what we have now is a 2-dimensional slice through the storm, and that's a vortex signature in 2 dimensions. What we find is the maximum outbound velocity, this is 30.5 meters per second, maximum inbound velocity, which is minus 28.5, I believe. And we can compute the delta V, we can compute the distance from here to here, and so on and so forth. Vertical association. For example, we have a mesocyclone, and we're detecting a vortex signature at 3 different slices. We then piece them all together like that. And finally, time association. This is a storm cell, by the way. We've got a location of a storm cell. It's past positions, so that thing is moving to the northeast, and then forecast positions every 5 minutes. Each algorithm also has a set of site-adaptable parameters. And what are these are used for is to tune the algorithm for regional differences, differences in storm type, and differences in synoptic and mesoscale regimes. And actually, this was intended for the site-adaptable parameters, but in actuality, I would love to cross that right off of here, because are there really regional differences in storms? Why are there regional differences in storms? Because of that right there. An example of an adaptable parameter is minimum rotational velocity to declare a TVS. So let's get into each of these big five algorithms. The SCIT algorithm, its objectives are to identify the location of storms, to forecast their movement, and to diagnose the reflectivity structure of the storm and its evolution. This is the algorithm that is now in Build 9, the fielded version of the WSR88D algorithms. What it does is searches for gate runs of reflectivity at various thresholds. There's actually 7 thresholds in the algorithm, and for the sake of simplicity, I'm only showing 3 here. And imagine the radar at the bottom of the screen, and along each radial, it picks up reflectivity data. So what it's finding are these are not shear segments, but storm segments in this case, and it's finding 3 different levels of them, 3 thresholds. And then it correlates these gate runs into 2D features. There's an example of one. And then finally, it does the vertical association with the 2D features and the time association between the volume scans. And here's an example of some of the output. I apologize, this is a little bit fuzzy on there, but I'll try to do my best here. We have a couple more slides here that zoom in a little more. But what we have here is a cell. That's a cell ID number. It's a 10. We have its past position, as I showed before, its track. We have the table showing attributes of the various cells. And over here we have trends of particular attributes in that cell. The cell table, what does it show? Well, it shows the top 20 cells that the algorithm is producing, and they are ranked. So the most severe cell is at the top of the table. They're ranked by 3 things, which the user can actually change the order of. They're ranked by the presence of a circulation or vortex in the storm, present or the probability of severe hail, and the damaging wind index. So for example, if you were running this algorithm in the Great Plains, you probably would rank the presence of a circulation first, and in the order I have here. But if you were running this algorithm, say, in Denver in the summer, where microbursts are the big problem, you might want to make this the first order of rank, the damaging wind index. We also compute a cell-based VIL. This is different from what's presently fielded, or what was presently fielded, which was the grid-based VIL. And this actually does the integration along the cell itself, so it takes into account some of the tilt of the cell. And we also compute the top of the cell based on the top of the 30 dBz cell component. So that's actually going to be a little lower than the Echo Tops product that's available right now, which looks at 18 dBz. And then here's an example of a trend of a parameter. This is maximum reflectivity of a particular cell with time increasing to the right, and this is over the last hour, showing the trend of that parameter. We can trend many different parameters in this manner. Next is the hail detection algorithm. This has also been fielded into the Build 9 version of the WSR88D, so that's being used right now by the Weather Service. Its objective is to estimate the probability of any size hail associated with a storm, and to estimate the probability of severe size hail, which is 3/4 inches or greater. It also estimates the size of the largest hailstones, and I underline largest because when the user uses this product and sees 2.5-inch hail, they should immediately click and say the largest stone that'll be found falling out of that cell, assuming the algorithm is correct, is 2.5 inches. There are going to be a whole bunch of other hailstones that are going to be smaller than that. And currently, we're using thermodynamic input from soundings in the field to determine the heights of the freezing level. In our real-time version, we're actually inputting these data automatically from the RUC model. What's some of the output here? Well, this is a little hard to see, but I'll zoom in a little more on the table on the next slide. But this is a case that hit Fort Worth, Texas in 1995. This was the infamous Mayfest hailstorm. You can see a lot of white in there. Those are reflectivities over 70 dBz, I believe. Let me go ahead to the next slide. This is the table, information in the table. We have probability of hail, probability of severe hail, maximum expected hail size, and also the cell icons that are overlaid on the screen are color-coded based on this probability of severe hail. And we use sort of the traffic light theory of green, yellow, red, with red being most severe. Next is the mesocyclone detection algorithm. This is the one that I've developed over the last few years. The objectives are to detect all significant vortices in the storm, with the exception of the tornado vortex, the more intense vortex. That's what the next algorithm does that I'll show. It diagnoses the vortex's strength, depth, and its evolution, and estimates the probability that the vortex will be associated with a tornado or severe weather within the next 20 minutes. And we expect this algorithm to appear sometime in the year 2000 or 2001 in the field. Well, basically similar to what I showed earlier, we find 2D circulations, we piece them together into 3D, but then the next thing we do is we take these 3D circulations and we classify and diagnose them. We use a number of rule bases. For example, if the circulation is 3 kilometers deep, it meets a certain strength criteria across that depth, let's classify it as a mesocyclone. We have a new classification. Instead of looking at an absolute depth, for example 3 kilometers, we look at a storm relative depth. If that vortex takes up 25% of the storm, let's say, but is less than 3 kilometers deep, we call it a low-top mesocyclone, and so on and so forth. We also diagnose the vortices. We do a vertically integrated strength over that vortex, and then the newest thing we're doing is using a neural network that inputs all the different attributes, for example, rotation, velocity, and depth, and outputs a probability that that vortex is associated with tornadoes or damaging wind. And finally, we track and display the mesocyclones. I won't say much about what's in the table here because that's a little hard to read, but I will say that there are 3 ways we overlay these vortices on the data, and they're circles, and the circles are proportional to the diameter of the vortex. We have a thin yellow circle, which is basically what we call a weak vortex. We have a thick yellow circle, which is one which has met the mesocyclone criteria, and a thick yellow with a red overlay on there, which is one that has extended to the base elevation of the radar, or 0.5 degrees. Or it exists below 3,000 feet above ground level for those that are very close to the radar, and that level is above the base elevation scan. One thing we developed, which has been very useful in the diagnosis of vortices, are time height trends. We're actually looking at, across an hour's worth of time and up about 35,000 feet into the storm, the value of certain parameters at each slice through that vortex. For example, in this case is gate-to-gate rotational velocity, and a little zoom in here shows 135 knots for this particular vortex. This is one that occurred in North Texas in 1995, one of the strongest ones we have in our database. Next, we have the tornado detection algorithm. Its objectives are to detect the intense vortices that are associated with tornadoes with at least a 10-minute lead time. So this is looking at more of the smaller vortices that are at times, sometimes within mesocyclones, at other times they're not, for example, with non-supercell tornadoes. We forecast the movement of the tornado, And this is important. This is different from the current fielded TVS algorithm and is expected to come out into the field sometime in the late summer of 1998, Build 10. I say this is different in capital letters for a reason. Those of you who have experience with the fielded TVS algorithm probably know that to get a TVS detection, it's extremely rare. You may see 2 a year in your office. Well, that's because that algorithm, as I mentioned earlier, was developed as a placeholder in order to develop this newer algorithm. The old algorithm just basically looks at a shear value in a mesocyclone. If it's reached a certain threshold, it calls it a TVS. But that's not really what a TVS is. A tornadic vortex signature is supposed to be the signature of this intense tornado-like vortex. And it's generally characterized as gate-to-gate shear, meaning we've got strong inbound and outbound velocities directly adjacent on radar radials. So that's what this new algorithm is looking for. And because of that, it doesn't require the presence of a mesocyclone to find a TVS. So it will hopefully detect non-supercell tornadoes. It's very similar to the mesocyclone algorithm, except it's looking at gate-to-gate shear. It does its 3D vertical association. It checks the size and strength of that 3D vortex to classify it as a TVS or a weak TVS or an elevated TVS if it hasn't reached a certain base height, which is at the 0.5 degree elevation or below 0.6 kilometers. And finally, it tracks and displays those. And this is what they look like on the screen. A red triangle with a letter on it. We also have a tornado detection algorithm table. It gives information about the location of that TVS, the base and the top, the depth, the gate-to-gate, delta V at the low altitude and also at the maximum throughout the vortex. And there are 2 types, the TVS and then the elevated TVS, and they're just shown in different colors, and they also show up as different colored triangles on the screen. Our final of the big 5 algorithms is the DD-PDA, and its objectives are to detect the occurrence of a damaging downburst with at least 10-minute lead time, 1 to 2 volume scans, to analyze the velocity and reflectivity structure of the cells, and to estimate the maximum expected winds in the downburst. And this is another algorithm we hope to see fielded in the next few years. And of course, this is the simple conceptual model of a downburst. Start with a reflectivity core aloft. You then get mid-altitude radial convergence, and in some cases we actually see some cyclonic rotation as a precursor to the downburst. And then finally, when it impacts the ground, we see a divergence signature in the radar data. And this algorithm, the prediction part of that, looks for the development of the core aloft and the rotation and the mid-altitude radial convergence. And for the detection part of this, it's looking for the divergence. Unfortunately, the detection part of this, it's usually, well, it's obviously too late by that point for a warning, since it's already happening on the ground. Well, I just said this. This is how the algorithm works. It's looking for strong convergence at 1 to 6 kilometers above ground level, a rapidly descending core, and the core has to initially start out rather high in the storm, some mid-level rotation, and actually takes into account a little bit of storm top divergence as well. And the downburst algorithm information is contained within the cell table under this column, and we have things color-coded based on their severity. If it's red, we're predicting a downburst in excess of 50 knots, which would be the severe criteria. Yellow would be in excess of 30 knots, or 30 to 50 knots, and so on and so forth. And we actually overlay information on the radial velocity data as well. An open oval is a prediction, and a solid oval is a detection. And also what's useful with the DD-PDA are the time height trends. This one over here shows a time-height trend of reflectivity in the storm. So you can actually see the descent of this reflectivity core with time. And over here is a time-height trend of convergence and divergence in the storm. So what we're seeing here, these negative numbers represent convergence. You see that developing in the mid-levels. And toward the end of this time, we see divergence numbers starting to show up here at the bottom. We also are seeing some upper-level divergence, too, at the storm top. Those numbers are a little hard to see. I apologize for that. We also have other NSSL algorithms that we've developed. We have a lightning association algorithm, which is actually a relatively simple algorithm. We're just associating cloud-to-ground strikes with the storm cells by a distance check. But by doing this, we can trend within the storm cell the rate of lightning, cloud-to-ground lightning within that cell. And we can also look at trends of the polarity of that lightning as well. We've developed a near-storm environment algorithm, or NSE algorithm, which looks at RUC model data, and that's used as input into some of the algorithms, for example, the hail thermodynamic data. It's also used to estimate the maximum parcel level of the sounding, which is a proxy for the storm top, and that can be used to determine relative mesocyclone heights and things like that. We have a velocity de-aliasing algorithm, and finally a velocity azimuth display algorithm, or VAD. Well, this one's not very easy to see, but this is the lightning association algorithm. The way we display this are with positive and negative signs in yellow over the radar data. We can trend the lightning flash rate in a cell. It's peaking right there. We can trend the lightning polarity rate. In this particular case, it's all negative. I think that's the positive percentage rate there. And the near-storm environment algorithm, its objectives is to provide real-time environmental information to the algorithms from the model data, which has 3 hourly upper air data and 1 hourly surface data. I think it's 1 hourly upper air data now with the RUC2. The data comes from the national centers to NSSL. It provides the thermodynamic information for HDA. Oh, and we also, this is something I left out, we can compute storm relative helicities for each storm using the storm's motion as predicted by the algorithm. Okay, what am I doing on time? Algorithm testing. There are 2 types of algorithm tests that we do. The first kind are offline tests or in-house tests. This is where we're actually looking at data that have already been collected in the past, and we're running the algorithms, looking at the output, and seeing how well it does. We can score the algorithms and so on and so forth. This is used to determine the skill of the algorithm. And there's 2 ways to determine the skill of the algorithm. There's detection skill, meaning how well does a particular algorithm detect the actual signature in the radar data. For example, how well does the mesocyclone algorithm find a mesocyclone in the radar data? And the second is diagnostic skill. Once a detection has been made, how well does the diagnostic part of that algorithm determine whether that detection is significant or not? For example, with the mesocyclone algorithm and the neural network probability of tornado, how well is it finding a high probability of tornado with mesocyclones that are actually associated with tornadoes on the ground? Then we have real-time tests. This is where we are running the algorithm in an operational sense in real time. And we started doing this in-house at NSSL, and now we are also doing it out of house at various National Weather Service offices around the country. So this helps us get some user feedback from the actual people who are going to be using these algorithms in the future. And we conduct these real-time tests with what's called the Warning Decision Support System, or WDSS, or WIDS for short. What is the WIDS? Well, the WIDS takes the RADS, which is the Radar Algorithm Display System, the sort of the front end to all this, where we can look at the algorithm output on top of the radar data, but it's attached to an automatic ingest system from the radar data. So it's actually processing this stuff in real time. We developed this basically for algorithm development in the early 90s. We wanted to see how well our algorithms are doing in real time, and then all of a sudden bright lights go on in our head and think we see some potential for use of this operationally. So in 1994 we developed a WIDS for the field and took it out to Phoenix, Arizona during the summer and conducted our first real-time test in actual National Weather Service severe weather warning operations. Now, Phoenix, Arizona doesn't sound like a place to go to test severe weather algorithms, but in the summer they do have a microburst hazard out there and a flash flood hazard as well. But we primarily used it for the damaging downburst stuff and the storm tracking. After that, we said, well, let's move on and take the challenge and go somewhere where the algorithm will really be, put to the real tests. So we took the WDSS to Fort Worth, Texas in the spring of 1995. And we got extremely lucky that spring. A lot of stuff happened, including that Mayfest hailstorm. 2 days after that, we had a long-track supercell in North Texas. A few weeks before that, actually, we had a supercell track across the DFW metro area and produced 2 tornadoes, one which was 3 miles south of downtown Fort Worth, and a second which touched down 1 mile west of downtown Dallas. They were pretty close. And the WDSS is a way to test our new algorithms and our new display concepts. So what are the objectives? Again, to evaluate the skill and operational use of our radar-based algorithms during real-time operations, to gain feedback from the Weather Service meteorologists on the display system before they make it into AWIPS. And what I mean by that is some of the concepts that we're developing will hopefully be found in one way or another in the operational AWIPS platform in the next few years. And finally, a biggie here is to foster collaboration between us NSSL scientists and Weather Service operational meteorologists. Oh, and this is a picture here, a bad picture, but it is a picture of the WDSS at the Fort Worth office. It's just the Sun Spark 20 workstation here. There are 2 other workstations running in the background together with this display system here, and it's sitting here between 2 of their PUP or WSR88D workstations. And the warning PC was directly behind me where I took this picture. Its components: there's a wideband radar data ingest system, so it's actually ingesting the raw level 2 data and not the level 4 products. And then it has all the algorithms, most of which I talked about already, but it also has a precipitation algorithm. We've developed a bounded weak echo region detection algorithm, and so on and so forth. And finally has RADs attached to the end, designed specifically for rapid access to all the algorithm information. Where have we tested? Well, these are all the places that we are now, with the exception of Pleasant Hill or Kansas City, where we're going by the end of this month. The system that's in Albany is going to be brought to Kansas City. But we are currently in all these sites around the country. Some of the sites are supported by different missions. For example, our site down in Melbourne, Florida is partially supported by NASA for some of their uses down there. The Phoenix site is supported by that electric power company out there for damaging winds and things like that. We have a site in Denver that's partially supported by the FAA for microbursts and other things. We've also been in other cities that are not on this list. This is just the current map, but we've also had the site up in Minneapolis. We were in Indianapolis for a few months. We were in Cleveland for snow algorithm testing. We were in Atlanta, Georgia in support of the Summer Olympics. And we were also in Charleston, South Carolina, also in support of the Summer Olympics. What has been the outcome of this testing? Well, one good thing New data is being collected from the entire nationwide network. We are no longer Oklahoma-centric in our thinking of what these storms are like, because we're starting to see storms from everywhere around the country and realizing that there is a whole myriad of different storm types that are out there. One thing we're also realizing is that the storm types that were common to parts of the country, for example, in the northeast U.S., there's the mini supercell. They don't just happen there, they happen everywhere if the near storm environment conditions are right. They just don't happen as much in certain places as others. We now have better and faster computers, so that means we can process a whole bunch more data. The DDPDA actually arose out of our testing out at Phoenix. We actually were out in Phoenix in a sort of a pre-test test in 1993, and from that test we developed the concept of the damaging downburst prediction algorithm, and that's when we went out in 94 during actual Weather Service warning operations. Of course, outcomes of this testing are the new algorithms that have already been delivered to the WSR88D. And finally, some of these display concepts will be ported into AWIPS. And this is just a timeline of the different algorithms and when they're going to make it into the system. As I said, the storm cell and hail algorithm are already in there. They went in 1996. The tornado algorithm is going in 1998. And then the rest of these algorithms, mesocyclone, downburst, this is a velocity de-aliasing mitigation algorithm, and a new vortex detection algorithm, which I'll discuss in a second, flash flood and dew polarization algorithms will finally make it into the system sometime at the beginning of the next century. By that time, the WSR88 system is going to migrate to what's called an open systems architecture, so they're not constrained to a really tiny, slow computer that was developed in 1979, what I call bell-bottoms technology. Anyway, WDSS stuff, how's that going to get to AWIPS? Well, one thing we tested last summer in Sterling, Virginia was something called SCAN, which is the System for Convection Analysis and Nowcasting, which is actually a merger of the WDSS that NSSL developed, some thunderstorm algorithms that the Techniques Development Lab at Weather Service headquarters developed, and an auto nowcaster that was developed at NCAR. And what was first gained by this test was, hey, we can use this SCAN as our prototype in AWIPS. But things have changed since then, and now NSSL is developing a limited WDSS functionality for AWIPS, which will be fielded in 1999, this path right here. It's going to be running things like the trends and the new tables and all that. It's limited in the sense that it's only going to be looking at product data, the level 4 data, not the raw level 2 base velocity data. So that's still a few years down the line. I wish I had a clicker for this thing. So what's the future of our algorithms? Well, there's so much that can be done with radar algorithms, and we're just sort of skimming the top of it. But some of the things we're starting to now look into are the use of artificial intelligence in the algorithm, advanced image processing. And one thing we are starting to think about for AWIPS is integrating algorithms from multiple WSR88Ds. You've got two radars looking at the same storm. It's going to see a little more information and decrease some of the uncertainties of what you're measuring if you're just using one radar. A multi-sensor integration, that's very important. Why just use the radar when there's so much more information out there that you can use to diagnose a storm? Lightning data, we're doing that a little bit already, and near storm environment data from the models. But what about satellite data? And we're also thinking about new paradigms with regards to vortex detection. In terms of artificial intelligence, our first foray into this is the use of the neural network on the mesocyclone detection algorithm. And what this is basically doing is we're taking a whole bunch of data from, right now our data case represents 29 different days from all around the country, and it's about 240 hours of radar data containing about 170 tornadoes. And it's looking at the mesocyclone detection attributes such as rotational velocity, depth and all that. And it's looking at ground truth data, whether there was a tornado or not. And that's a whole issue, by the way, in and of itself, but we've got to start with something. And the neural network just, I can say this much, chunks through all this data and comes up with this big formula, which then can now look at an independent data set, look at data it hasn't seen, and determine a probability that a new detection is associated with a tornado or damaging wind. And right now it's not doing too bad. It's actually doing better than the old classification schemes that were in the algorithms, the schemes that determine whether something was a mesocyclone or not. And this is real important because we're finding a lot of vortices and storms that are below the criteria for this, mesocyclone as developed in the 80s, looking at Oklahoma data. We're also finding mesocyclones, obviously, that don't produce tornadoes. But there's a whole bunch of other information in there that's important, and the neural network is helping find some of that stuff. Image processing, new and advanced. Well, I'm showing an example here of what's called the machine intelligent gust front algorithm. This is something we haven't developed. This was developed out of MIT in Boston. But what this is basically doing is a new way to try to pick out certain signatures within the radar data by passing what are called templates, little boxes over the radar data, and coming up with what is called an interest field. So this little box that's being passed over this data is looking for a line or a thin line. And that's reflectivity data, and that's what you can sometimes see as a boundary and as a gust front or something like that. And it comes up with these interest fields, does a little bit of filtering, and actually can look at the past history and predict the motion of that gust front. What we'd like to do is take something like this idea and adapt it to 2D vortex detection. We've actually done something like this, but the amount of computing time it does to just look at one volume scan is much longer than it takes just to collect those data right now, so we've got a ways to go. We have another form of image processing in the form of our bounded weak echo region algorithm, and this is actually looking for these concave features. This is a cross-section through a storm that is capped by high reflectivity and surrounded by high reflectivity as well. And this algorithm uses a fuzzy logic scheme, so it's actually assigning confidence levels in terms of probabilities of whether there's a bounded weak echo region there or not, and color codes based on those confidence levels. Multiple radars. We want to integrate output from several WSR88Ds. As I said before, this decreases the uncertainties in the measurements. Let's say, and it fills in gaps in the data. And for example, let's say a storm from one radar is in what's called the purple haze or the range folded echo, but from another radar it can see it fine. So you want to fill up those gaps. And this is important for Weather Service offices where more than one radar covers their county warning area. So we really want to develop algorithms that cover their entire county warning area. Multiple sensors, again to decrease the uncertainties and fill data gaps. For example, let's say a storm is obscured by the mountains west of Denver. If we integrate satellite or lightning data into this algorithm, then we'll know something is there, because the radar doesn't provide the complete pictures to the puzzle. And finally, I wanted to discuss a little bit of the work that I'm doing now with the vortex detection and diagnosis algorithm. What we're doing is we're integrating ideas that we are learning from the new radar data. So we're collecting all these new cases from around the country and learning a whole bunch of stuff about vortices and storm scale vortices and mesocyclones that we never knew before when we were just looking at them in Oklahoma. We're also collecting data from the near storm environment and satellites and all that. And we want to integrate all this to detect the entire spectrum of storm scale vortices that range from the mesocyclone, big rotating updraft scale, to the TVS or tornado scale, and all things in between. Because there are things in between. For example, one of my favorite slides here, this is an example of your classic central Oklahoma supercell from RADS. It's a pretty big storm. It's got its hook echo there. I've got overlaid the mesocyclone detection output on there from the velocity data. And there's an F4 tornado on the ground with this at the same time. Now we have these kinds of things, these mini supercells. This is one that occurred in eastern Colorado. There's the overlay from the mesocyclone algorithm. As you can see, it's now a thin circle, which means it's found a weaker vortex in that storm. This cell is about 1/3 to 1/2 the size of the cell to the right. These are both at the same zoom factor, so it shows the relative difference in size in some of these storms we're seeing. Hold on to your seats. That is also a tornadic supercell. F1 tornado on the ground at that time. This is the same zoom factor as these two other storms. This one occurred out in Phoenix, Arizona in 1995. That entire reflectivity core can fit inside that mesocyclone. Other issues to consider. First one there, region versus near storm environment. I already harped on that. There's this general overall feeling that certain parts of the country are being ignored by NSSL in their development of the algorithms. And let me tell you, we're not ignoring these different parts of the country. We really want to learn about what's going on out there. The problem is, the storms don't happen as frequently out there. So there isn't that much data yet to look at. But the other important thing is that these differences aren't really regional differences in the storms, but they're regional differences in the climatology of the conditions that produce these storms. Like I said, in the Northeast, you get the conditions favorable for mini supercells a little more frequently than, say, in Oklahoma. But it does happen in Oklahoma once in a while, and the big giant storms do happen in the Northeast once in a while. Witness May 31st, 1985. I don't want to go ahead yet. Flash flood warnings. We've never really touched on flash flood warnings until this year, so we're actually starting to do some development in that area. Polarimetric radar algorithms. These are dual polarization radars that are actually looking at the polarity of the different precip particles. And in a nutshell, you can determine precipitation type, snow, hail, wet snow, and so on and so forth. You can also use this for advanced flash flood detection techniques and things like that. Terrain's an important factor, especially out in the west. One of the things we're finding with the hail algorithm out in the west, especially with radars that are sitting on top of 8,000-foot mountains, is it doesn't do as good, because it's assuming a flat earth, first of all, underneath that radar, or a flat curved earth. And it's also assuming that the earth comes out from the radar at the level of the radar. In some cases, the radar is well above looking what it's seeing. New volume scan strategies. Right now, volume scans update 5 to 6 minutes at a time. We're thinking of volume scans that update every 3 minutes, or ones that send out a pulse every half a degree in azimuth instead of every 1 degree, and so on and so forth. And this is a big thing. We want to expand our database of storm cases. We want to collect, well, we really want to collect and be able to look at everything that's out there, which is not that easy of a task, but we are collecting a lot of data. And right now we have data in-house of over 1,000 tornado cases. We've only looked at about 15% of that. So finally, to wrap up, our mission in the SWAT team at NSSL is to develop new severe weather warning applications that enhance the capability to warn for life and property-threatening weather. And we're hoping this is all part of the entire integrating warning process that gets people to eventually take cover in their hallway in the middle of the house while the rest of their house blows away. That's from Kissimmee, Florida, if you don't see that. That's it. Any questions?
Before we open up the questions, we were talking in Phoenix about how you've been working to get the probability detection almost at 100% and the false alarm rate is going to go up. Could you just talk about what you're doing there?
Well, what Paul asked was talking about increasing the probability of detection of certain signatures, but at the expense of increasing the false alarm rate. And Paul and I were talking in Phoenix about this with regards to the vortex detection algorithm, which is what I'm developing. I've developed the algorithm in such a way that I wanted to be able to detect every single vortex that's out there and then diagnose that vortex, whether or not it's going to be tornadic or severe. The old paradigm of the algorithm was to apply these thresholds right at the very beginning of the vortex detection, so it actually started throwing out some of the shear segments because they didn't reach this criteria. So a lot of these vortices were just plain not being detected or being missed. So what's important, I think, in my opinion, is to try to find them all, and once you've found them all, try to then say, okay, which ones are important and which ones aren't by diagnosing all the different attributes. Questions?
You talked about cell trends, and you obviously have much more data than trends in what is in Bill 9 right now. In the recent weather and forecasting article said the cell trends in Bill 9, is that reliable because of the elevation and the...
Yeah, there are.
Would you agree with that, and until you change the patterns?
Well, that is an unfortunate artifact based on the limitations of the Doppler radar, because it's only scanning at discrete levels throughout the storm. For example, if a cell top is happening between this elevation scan and that elevation scan, you don't really know where in between that's happening. So the first step we've taken with that is to take our trend displays and actually plot overlaid on the display, for example, of storm top, the uncertainty or the width of the possible area where that storm top could actually be. So.
Just out of curiosity, how long does it take for the algorithms to run through and flip the little circles or whatever?
Well, on our system, we're running it on a Spark 20. An elevation scan takes about 30 seconds to come in real time. The algorithms run on that elevation scan in a second or two, so they're rather fast. So. Any other questions?
Yeah, I understand at the beginning of your talk that Doppler radar can give us a probability of a tornado striking a certain area within a given time?
Well,
80% or 20 or whatever you said?
it's the attributes of what we're seeing in the Doppler radar field that we're using to determine that probability. So we first detect the vortex and then say, okay, if this vortex is this deep or this strong, what's the probability that there will be a tornado associated with that vortex in the next 20 minutes? The next 20 minutes part comes from the fact that when we're training the neural network, we actually call a vortex tornadic if it goes on to produce a tornado within the next 20 minutes, or it's happening right now. So.
Warnings issued based on those statistics?
When we're testing the WDSS in real time, they are using that probability output along with a bunch of other outputs, since they're integrating a bunch of information to issue their warnings. So warnings aren't based on just that one probability number alone. They're looking at a whole bunch of other information.
You're talking about the new algorithm with the low top, where you have 25% of the depth. And I was wondering, when you talk about probability, now if the storm is too far, the radar to really be able to detect that 25%. I mean, you also talk about negotiating maybe satellite data and whatever else in there. How well is that going to work together? If the scan is not able to see that and trying to do probability and having a forecast.
That's going to be one of the big challenges. Any storm that's not... His question was, if we have a low top storm that's too far from the radar, how are we going to integrate the other data to look at that. And that's going to be a big challenge, obviously. So if we can't see everything we need to know about that storm, our uncertainty on that storm is going to be a lot higher.
Chuck was talking about the probability of warnings, and it would be bad if the radar's saying, well, 30% chance of wind damage or whatever, and the forecaster sees that and puts out a warning with only 30 or 40% probability, and the next thing you realize it's some F2 tornado. They're going to a town or whatever. I don't know. It seems like that would be more probabilities would be wrong there, almost, rather than just issue a warning based on the kind.
Okay.
Al, is Al here? No. You step outside. You use some of the stuff in Fort Worth. You just kind of...
Yeah, I was going to wait till tomorrow, but it's great stuff. For instance, with hail, what we try to do is use the output from RADS along with our own analysis of the three-dimensional structure of the storm. And we found that often the hail, there's a great match with the estimated hail size if we have good structure, i.e. good overhang and or a beadwood or something like that. There are times with marginal shear cases when RADS makes some overestimates of hail size. And then we don't see that much structure with the storm. It's reflective of the fact there's really not that much shear. We have a tall core, maybe more heavy rain than hail, and sometimes with that, with just marginal shear cases, we'll get an estimate of 2-inch hail, we actually get 1-inch hail. So we're learning to use the two together, and you can't just use any one piece of input. You know, the RAD stuff is great, but you've got to look at manual analysis of the radar, knowledge of the environment, and so on. But those algorithms are so far superior to the original algorithms, it's almost no comparison. And they are improving.
You know, I think based on what Al's saying and what Matt was talking about with some of the shortcomings of this, is that they continue to work improvements of this, but there's always going to be the false alarms, and there's always going to be the undetectable severe events. And I think that's just the game. I mean, we as meteorologists know that the WSR 88D is not an end-all, and somehow if we could just get it to the media that it's not going to be, and we're just sitting there scrapping, trying to improve it as best as we can, but it's still never going to be perfect in that idea.
The fellow down here asked a question, what about a distance, great distance from radar for a low-top supercell? You're going to depend on spotters more in a situation like that. The further away from the radar, the more dependent you are going to be on spotters. You always have to have the two working in combination.
Yes, I was going to know what Nessel's doing about, and maybe you have one attack already, about a wind shear algorithm for the aviation community.
We've done some work in the Gusfront algorithm arena where we've looked at wind shifts along wind shift gust-front lines and things like that, estimating the wind speed and direction on both sides of that. For the microburst algorithm detection, the actual one that's used for aviation interest, most of that development has taken place outside of NSSL. The damaging downburst algorithm that we've done is more tuned for public warning and weather service warning and not aviation interests. There's also a system that's been developed in concert with the radar data called LWAS, a low-level wind shear alert system, where they have the anemometers along the runways and they use that with the radar data to warn the pilots in the terminal area. So a lot of that work's done up at NCAR and MIT. Any other questions?
Okay, thank you, Greg. tomorrow for the seminar. Chuck, did you want people to sit in the front tomorrow?
I want every seat in the front filled up from the front back. If anybody is sitting in the back by themselves, we won't even start. Until all the seats in front are filled up, I'm not even going to bother starting.
Please, people, just do it. Tomorrow morning also, before you come in, there will be boxes where you'll pick up a clipboard so that you'll have a nice hard writing surface. So just pick that up on the way in. If there's any other problems, address them to me. If not, I will see you tomorrow morning.
Yes.